Hello student, let us start with the next topic of our syllabus, that is nothing but a moment of inertia. As might be all of you are well known about law of inertia. Newton's first law of motion is said to be law of inertia. Every body remains as it is unless and until we have applied some unbalanced force on it. Why this property remains as it is? Because it has some mass, and that mass we call here inertia. That's why the Newton's first law of motion sometimes said to be law of inertia. Because of mass of this body remains here. It can't displace by its own because it has mass, or we can say it has inertia. Now let's see what is moment of inertia here. Moment of inertia is one of the quantities similar to that of mass. Now we know there are different type of motions: translational motion as well as rotational motion. Whenever there is translational motion, object move from one point to other point directly, that is said to be translational motion. There is a mass work as an inertia. Rotational motion, object is here, it is rotating about its own axis like this. If this object is rotating here, there must be some opposition to this rotational motion, and that opposition was done by mass, and that mass here in this rotational motion is said to be moment of inertia. To get in detail, let's start with one derivation. So this moment of inertia is a topic. First of all, to explain this, we must derive one equation that is said to be equation of kinetic energy of particle performing rotational motion. Equation for kinetic energy of particle or body performing rotational motion about its own axis. So let's start with this body. Any irregular shape body we can take, just like an amoeba, any shape. So this is a body, and this body is rotating about this axis of rotation. This vertical is axis of rotation, about this body is rotating. Now let us consider this body consists of n number of different particles whose masses are m1 first here. m1 is the mass of first particle kept at distance of r1 from origin O, or from point O. Then second mass m2 kept at distance of r2 from origin. Third mass m3 kept at distance r3 from O, so on up to nth mass is mn kept at a distance of rn from a origin O. This is a situation, and this axis is passing from the body and it is perpendicular to the body. For example, this is any random body and this is axis. This axis passes perpendicular to this, like this. This plane becomes axis of rotation, and this duster becomes a rigid body. It is rotating. It consists of large number of small particles, and they kept at a distance of r1, r2, rn from axis of rotation. So the point O we are getting here in this figure, it is a point from where the axis of rotation get passed. Now let's start with this. So here it consists of n number of particles kept at distance of r1, r2, rn, so on. Now we know that as this body, whole body is rotating, just see omega, this omega is angular velocity with which body is rotating like this. Body is rotating like this with angular velocity omega. Now here our aim is to find the equation for kinetic energy of particle which is rotating, means this body is rotating, we are going to find out its kinetic energy in rotational motion. But we know the equation for kinetic energy in translational motion is known to everyone. So this is E is nothing but a symbol used for translational kinetic energy. So we can represent translational equal to 1 by 2 m into v square. M is the mass of the object or body, v is the velocity with which it is moving. Now this is a translational kinetic energy equation. So mass m1, as this is rotating, this also rotating about the axis like this. m2 is also rotating like this. m3 is rotating like this. So on up to mn is also rotating like this. As if we consider these circles are of different radius, so accordingly still the whole body is moving with a constant angular velocity omega. Every particle is moving with a different linear velocities because they have to cover a different circle. The first circle is small, velocity v1 is small. This m3 circle is bigger little bit, means what? It has linear velocity larger than v1, and so on. And that means what? When this body is performing rotational motion, different masses kept at different distances from axis of rotation, they are rotating about this axis with different linear velocity. This is angular, these are the linear velocity. Let us assume that first particle having a mass m1 kept at distance r1 from axis of rotation, rotated with a velocity, linear velocity v1. Second is having a v2, third having a velocity v3, so on up to nth particle has a velocity vn. Linear velocity we have just written. So we can write one equation as just we have written here. So same thing I will write here. So we can write simple equation. The kinetic energy is equal to 1 by 2 m into v square. Okay, but in for first particle it is m1 v1 square, and that is kinetic energy E1, KE1 for first energy, kinetic energy of first particle 1 by 2 m1 v1 square. Same thing can be written as 1 by 2 m1, as we know there is equation v equal to r omega, so v1 equal to r1 into omega, put it here. So what we get, m1 r1 omega. So this is the kinetic energy of first particle. Similarly, what is kinetic energy of second particle? KE2, 1 by 2, directly I will write this m2 r2 omega. So just there is one little modification. So it is v square. So v1 square equal to r1 square omega square. So this must be the square terms. Okay, let's go for third, fourth and so on up to nth. Directly I will write the nth. Kinetic energy of nth particle is equal to what? 1 by 2 mn rn square omega square. Is that clear? So these are the kinetic energy we have written for first particle, second particle, so on up to nth particle. Now what is our aim? Our aim is to find the kinetic energy of whole body which is rotating, and these are the kinetic energy of individual particles having a mass m1, m2, m3, so on. That's why the total kinetic energy is nothing but what? Sum of all this kinetic energy. So we can write one equation, I will write it here. So E kinetic energy of rotational motion equal to, for whole body which is rotating, equal to kinetic energy of first particle plus second particle plus so on up to plus kinetic energy of nth particle. So just add them. So add all these things. So what we get, first 1 by 2 m1 r1 square omega square plus 1 by 2 m2 r2 square omega square plus so on up to plus 1 by 2 mn rn square omega square. So these are the total kinetic energy of the particle E1 plus E2 plus so on up to En. Now in this case 1 by 2 is common and omega is common. Just see 1 by 2, 1 by 2, 1 by 2. Omega square, omega square, omega square. So we can write the same equation as, we can write same equation further here as, just little bit we can write the equation by taking these quantities, common things common, and just rewrite the equation again. So what we get here, just I will write it here again. Okay, so just take this common. So we can write this as total rotational kinetic energy 1 by 2 in the bracket m1 r1 square plus m2 r2 square plus so on up to plus mn rn square. These are in bracket, 1 by 2 is common, omega square is remaining, omega square is common. Now this bracketed term is nothing but what? Addition of all these things, product of mass into distance from the axis of rotation for all particles, their addition. So you can write this as equal to 1 by 2 summation of I varies from 1 to n mi ri square, and this can be written as I equal to 1 m1 r1 square plus I equal to 2 m2 r2 square up to what? Up to n into omega square as it is. This is what? Rotational kinetic energy. So kinetic energy that is said to be for rotational motion. Now here this bracketed term I can put one symbol. So you can write here it as 1 by 2 I into omega square. So rotational kinetic energy was given by this formula. Rotational kinetic energy equal to 1 by 2 I omega square. Here this I is what? I is said to be moment of inertia. I is said to be moment of inertia. And what is this moment of inertia means? Product of mass of the particle into distance from the perpendicular axis or distance from the axis of rotation, its square. Product of mass of the particle and square of distance from the axis of rotation. It is said to be moment of inertia. Now this moment of inertia and this kinetic energy for whole body performing rotational motion. Translational kinetic energy I will write here like this. Trans means what? Translational. It is 1 by 2 mv square. If you compare these two equations, see, it is kinetic energy, it is kinetic energy. Rotational motion, it is translational motion. 1 by 2 common, it is number. Here omega square, angular velocity square because it is angular motion. Linear velocity square because it is linear motion. Translational is linear motion. Now here it is I and here it is m. So in translational motion, there is a mass m. And in rotational motion, same mass is represented by I, and that I is said to be moment of inertia of the body. So here in translational motion, the body cannot move from its own position because it opposes by one part, that is said to be mass, that is said to be inertia. Here rotational motion get opposed. It cannot automatically rotate anything. Why? Because there is a I, moment of inertia, equivalent to that of mass. So this is nothing but a moment of inertia of the body. As common sense, if this is I, what is the unit of I? Kg meter square. And mass can be measured in kilogram. And distance square means meter square, kg meter square, or gram centimeter square. These are the unit of this. Similarly, you can find dimension of this. L to the power 2, m to the power 1, t to the power 0. That is dimension of this. That is nothing but dimension of moment of inertia. Now remember, under this heading moment of inertia, 2 points we have seen. The first one, we have derived the equation for rotational kinetic energy. Rotational kinetic energy of body which is performing rotational motion about its own axis of rotation. That equation we have derived, and that equation we have compared with the translational kinetic energy equation and equate them. So this mass is equivalent to I. So I is said to be moment of inertia. Now the question would be there. Why it is not said to be mass? Because the motion is different. Here it is mass in translational motion. Rotational motion, it should be same work. This I perform the same work as that of mass, but it is said to be moment of inertia. That's it. So these are nothing but what? Moment of inertia of the body. Now remember, before going further in detail of this, just see this diagram. In this diagram, if you see, here we have considered masses m1, m2, m3, m4, so on up to mm. The body consists of n number of masses, m1, m2, so up to mn. But if we have the body, such another type of body, in that body, it is not possible to distinguish the masses. We know only the total mass of that body or small mass of the body we can find out. In that case, suppose this is another body, just I will draw it here. Suppose I will draw the smaller one. This is another body. This is a body which has different masses, m1, m2, mn. This is the body which doesn't have different masses, or we can't identify different small particles. So this is said to be discrete body in which different particle can be identified. Here it is said to be continuous body. We can't identify the particle. In that situation, what should be the formula for moment of inertia? We can't identify the particle. Let's consider any point. Here let's consider its mass dm at a distance of r, suppose. In that case, the equation for moment of inertia here, moment of inertia was given by what? I will write it again here. Moment of inertia of a body performing rotational motion can be written as I equal to summation of I varies from 1 to n mi ri square. This equation for moment of inertia. Equation for moment of inertia. Okay, if body consists of discrete particle. If body consists of discrete particle like this, but if body consists of such continuous particle, then you can represent this I equal to summation would be replaced by integration. Mass would be replaced by dm r square as it is. You can write r square dm. What is the difference? Summation is used when we can identify different particle separately. That summation gets replaced by integration if in the body is homogeneous, perfect homogeneous, we can't identify different particle. Summation replaced by integration, and mass mi replaced by dm. R square remains same, unit remains same, and its dimension also remains same. So this is nothing but a moment of inertia. Now the next topic of your syllabus is what? Moment of inertia of the ring. They have find out moment of inertia of the ring, thin uniform ring. So what exactly it is for ring? Moment of inertia of a ring. Now this ring means what? It consists of such type of circular shape, and that is nothing. Suppose it is circular ring. Suppose it is circular ring, and this is the center of that. Suppose center is O, and this is the ring. Okay. If the axis is passing from the center such that, suppose this pen, this marker is an axis. Axis is passing like this, passing from the center of this disc perpendicular to its plane, and whole mass of the disc, sorry, not a disc, it should be ring. Whole mass of the ring is concentrated along the circumference of a circle, and this axis of rotation passing from the center of the ring and perpendicular to surface of the ring. In this situation, what is the moment of inertia of this ring? That they have given directly here. Moment of inertia of this ring is I equal to mr square. This I equal to mr square, where m is a mass distributed along the circumference, mass of the ring. R is nothing but a radius of this ring. Then the moment of inertia is mr square by this formula. Mass into square of distance, m into r square. That is moment of inertia of a ring. Apart from this, if the object gets changed, if instead of ring we will consider a disc, what will occur? Definitely moment of inertia gets changed, and that we have to find out now. This moment of inertia of a ring. From this we have to find out moment of inertia of a disc. Disc is nothing but what? Disc is a solid surface. It is a hollow one. Ring is hollow one. Disc is a solid one. So suppose this is a first ring. Again another closer rings. If you put, it becomes disc. Now this become a disc. This consists of solid part. Now we have to derive the equation for moment of inertia of a such a disc we want to derive. So before going in detail, just turn the page of your book, and if you see on that page they have mentioned there the symbol, another topic is there, that is nothing but a moment of inertia of a disc, mi of a disc, moment of inertia of a disc. So in your book they have drawn one figure, so I will draw it here like that. So such type of diagram they have drawn. So suppose this is a disc, whole disc. Let us consider this disc consists of small part, smaller disc together, and if we added that disc together we get a total disc. So let us consider any small disc inside this. Let us consider this axis of rotation. Just I will write down this axis of rotation. It's got a little bit tilted. Just make it correct. It actually, let's go make it exactly vertical. So I will draw it again. So let us suppose this is axis of rotation. Now here this inner disc is like this, and this inner disc has some thickness. Suppose it has some thickness dr. Dr is the thickness of this inner disc, and distance is this. Distance they have mentioned small r, I think. Yes, it is small r is a radius, and capital R is a radius of whole disc. Capital R is radius of bigger disc, whole disc. Whole disc consists of smaller radius disc together. It will form a bigger disc having a radius capital R. Now here, before again, this is a concept. This is the axis of rotation passing from the center of a disc. Okay, suppose it is passing from center of disc, and this bigger disc has a radius capital R. And let us consider inside this bigger disc, it consists of large number of small discs combined together, so it get converted into solid form. Let's take one of the best example for this. Suppose we have a plate, circular plate. Cut the plate having a little bit less radius. First make a radius 10, 9, 8, 7, 6, 5, 4. Such type of cutting we will do with a plate, solid plate. What we get? The 8 or 10. 10 radius means what? It is a ring with a radius 10 centimeter. 9 means another ring. 8 means another ring. It consists of large number of rings. If we put the rings together again, it will form a plate, and that is nothing but this bigger disc having a radius r, this small part having a radius small r. Why we have seen this? We will see that later on. Let's go further. Here, before going into that much detail, let us consider one concept, sigma. Suppose sigma, or we can say rho or sigma we can take. As in your book they have taken sigma, we'll go according to sigma. So let's start with the sigma here. So it is sigma is said to be mass divided by area. Mass per unit area is suppose sigma, and this is said to be, or in short we can write m divided by a. Mass per unit area. It is said to be surface area of a disc. Surface area of a disc. As it is a disk, so we can write for this disk sigma equal to, suppose mass of the disk is capital M and area of the disk is what? Pi r square. M divided by pi r square, that is nothing but a surface density, mass per unit area of this disk. Now let's go further. Now let us consider this whole disk consists of one small disk having a thickness dr, having a mass dm, having a radius small r, having a radius small r. See, basically this is passing from the center axis. So this axis must pass from the center actually. So suppose here somewhere it is center and this is the axis passing. Now this is r, this again r. Okay. Now let's see. So this inner disk consists of mass dm, radius small r and having a thickness dr. What is the area of this then? The circumference of a circle 2 pi r into width of the circle, it is dr. So we can write this sigma for inner disk. This is sigma for outer disk, or in general we have written. For this sigma equal to what? Mass divided by area, and that is nothing but what? Mass divided by area means length 2 pi r into width dr. 2 pi r into dr. What is mass of this? dm we have assumed. So you should write here dm divided by this, dm divided by this, and this is sigma equal to. From this find out the value of dm. So this equation implies that dm equal to what? 2 pi r dr into sigma. This term go to this side. dm equal to 2 pi r dr into sigma. So this will give what? Mass dm. Now just here, this whole disk consists of small disk, small inner disk, and the radius varies from here. When it comes here, it is what is value of capital R? 0. 1, 2, 3, so on up to capital R. So this R varies from 0 to small r, because this small r, na, it is varies from r equal to 0 from center to what? At the end, r equal to capital R. So to find out its moment of inertia, we have to use the equation that is nothing but just simple moment of inertia formula. We know that formula we will use, and we will take its integration because it is mass dm, not a continuous distribution of mass. So let's start with. So we can write here. I will write a little bit this side. Okay. So I will write to this side so you get better understanding of the same concept. So we'll go to this side. Okay. So here I equal to what? Our formula, mass into square of distance. Mass into square of distance, that will give the moment of inertia. But in our case, mass is what? dm. So we can write this as dm into capital R square. Or we can just use a small r square. So just according to book we'll go to dm into small r square. So that is moment of inertia of a disk. Okay, inner disk, smaller one, this dark one. It has moment of inertia dm. It has mass dm. It has radius r. So it is r square. Moment of inertia of inner disk. Suppose I want to find out moment of inertia of total disk, all this bigger disk. Then we should consider r varies from 0 center to capital R. So in that case, that moment of inertia, this is moment of inertia for radius small r. Let's find out total moment of inertia. It can be find out by taking integration of IR, where r varies from 0 to capital R. So go further, put the value. So integration r varies from 0 to capital R of dm into r square. Put the value of dm now. Just we have derived initially here to this side. We have derived this value dm. Put it there and rewrite the equation. So I will write here. So equal to integration r varies from 0 to capital R. dm is what? 2 pi r dr into sigma into this r square. Okay, into this r square. In this case, 2 pi is constant, sigma is constant. Take it outside. So we can write the same equation as, I will write it further here. So we can write this equal to integration r varies from 0 to r. So here First, we will take common terms. Constant terms should be taken outside. So same equation can be written as 2 pi sigma integration r varies from 0 to r of, this is r square and this is r, it is r cube dr. Integration of r cube is what? R to the power 4 divided by 4. Those who don't have mathematics, don't worry, this simple mathematical formula. R cube integration is R to the power 4 divided by 4. So same equation can be written as equal to I equal to. So here we have written this part. Let's go further. Just we'll go refer the book. We can find out like this also. But it is better to look at a book. So we can write here 2 pi sigma r cube dr. Just look at a book so that we get here that equation. And if we solve it further, we get 2 pi sigma r to the power 4. Basically, it should be small r to the power 4 divided by 4. Limit varies from 0 to capital R. Such type of equation we get. Now, what are the limits? Put a capital R first, then put a 0. So, what we get? Capital R square by 4 minus 0. So, if we remove the limits and directly write the capital R, doesn't matter. It is same. R to the power 4 divided by 4. Same thing was done in your book. Directly they have written r to the power 4 divided by 4. Now let's here, just we have to put some values. Let's here put the value of the another parameter. I will put it downward because the equation goes a little bit downward. So let's go downward direction. So here in this downward direction, let's put the values now. Here 2 pi as it is, so I will write this as 2 pi as it is, I will write this as 2 pi. Now the sigma, if you remember, we have already find out the value of sigma in general for bigger disk. I will show it here. See, sigma already we have find out here. M divided by pi r square, that is sigma for whole disk. So put that value of sigma here and rewrite the equation. So let's write 2 pi as it is. Sigma is what? That sigma just already I have shown you. It is M divided by pi r square, bigger disk. So m divided by pi r square into r to the power 4 divided by 4. So this is the equation we get. Now let's see, this r square cancel with this 4, it becomes square here. Okay, 2 cancel with this 4, it becomes 2 here. So what we can write, this pi get cancelled with this pi. What is remaining? 1 by 2. This term get cancelled, m into r square. So this I equal to 1 by 2 m into r square. That is the moment of inertia of a disk. I equal to 1 by 2 m r square, moment of inertia of a disk. So in this fashion, we have find out moment of inertia of a whole disk here by just we know the moment of inertia of a ring. Then we go to disk. Disk consists of smaller inner disk like this. First find out mass dm. Let us suppose mass dm, radius small r, thickness dr. Put the values, find the value of sigma, find the value of dm that we have find out here. Then just go to this moment of inertia. Total moment of inertia, r varies from 0 to r. We have solved it like this. Final equation we get. Moment of inertia per disk is what? 1 by 2 mr square. You have to remember this 1 by 2 mr square for disk. And for ring it is simply mr square. So that you have to remember. Moment of inertia that we have derived up till now. Let's go to the next topic and then we'll stop today. The one topic we'll cover because the next topics are different. So let's start with the next part of this same topic, and that is nothing but what? Radius of gyration. What exactly radius of gyration means? And radius of gyration can be represented in terms of, it is one of the significance of the radius of gyration is a concept that is said to be significance of that moment of inertia, or we can say it is one of the basic physical significance of moment of inertia. So let's start with that particular next topic, radius of gyration. I will write down here. So radius. So let's start with radius of gyration, and this radius of gyration is represented by letter K. So let's start. So see, here whenever we find the moment of inertia means what? Before going into detail of this and moment of inertia also, we start with one of the best example. Same thing they have given in your book. Suppose when we went to any lab, lab or suppose some cabin we go. So there is one door, and to this door, suppose I will draw that door. So this is the door of that cabin or computer lab. Here there is a handle. On this handle they will mention here the word push. Push or pull they will mention here on this handle. So this part is fixed. This edge of the door is fixed. So when we push it or pull it, push or pull is mentioned. Push it or pull it, door get open. Now remember, whenever we apply some force here, while pushing or pulling, or someone use a pull word. So here, when we push or pull here, what we are going? We are going to apply some force on this part of the door. Now, how much force is required? That depends on two factors. What are the two factors? First factor, mass of the door. If door is very heavy, we have to apply a little bit more force. Mass of the door. First factor on which the force applied depends mass of the door. Second factor, place where we apply the force. Place where we apply the force. That is also matters. If we apply the force at wrong place, a little bit toward the axis, it is seen that force required is much more. So that place where we apply the force, that is also important, and mass of the door also important. Mass of the door is suppose it is also important, but we are interested in the place. Why we are interested in the place? Suppose this push word is here, we can push it here. If you apply small force, you can open or close the door. But if the word, this push word shifted here, instead of this place, if it is here, I have just attached this handle here. Instead of here, I have attached it here, inner side. What will occur? More force is required. Again, if someone is there, nobody will do like this. But suppose someone attached the handle here, and here they have mentioned push. Can you imagine? Very huge force is required to open the door here. And that is the reason why always push button or this handle with this push word is kept near to the other edge here. Why? Because when we apply the force here, we can do the same work. We can open or close the door with a small amount of force if the handle is here. If handle goes inside toward this axis or fixed part, applied force required is much more. Is that clear? And that is very important here. And that can be explained here. One concept here, it will explain the amount of force required depend on distribution of mass, how the mass is distributed, and that can be measured by using one quantity, and that is said to be radius of gyration. So let's start with this radius of gyration. So here, suppose any object is there. Suppose we will consider this as a ring, and this is axis of rotation passing from the center of the ring. We know the ring mass is exposed within this part. Within this part, it consists of mass. Mass is distributed along this, or we can say this is radius r. So we can say in this case, the mass of the ring is distributed along the circumference of a circle. Circumference of a ring. Mass of the ring is distributed along the circumference of a ring. So the distance from this mass to the axis of rotation, we call it as a radius r, and this radius itself is called as a radius of gyration. Instead of r, they will use the symbol k. How the mass is distributed? Near to the rod or away from the rod? Rod in the sense axis. Whether the mass is distributed near to the axis or far away from the axis, that can be explained by using one parameter, and that is said to be radius of gyration. If radius of gyration k is small or r is small, what will occur? This place, here it is a initially ring. If k is small, it comes here. Mass distributed close to the axis if k is small. Mass distributed away from the axis if k is large. And that is nothing but a radius of gyration gives the parameter that gives us to understand whether the distribution of mass is near the axis or far away from the axis. Is that clear? Apart from this, let's go to moment of inertia now. Now moment of inertia, we know it can be represented by mr square. Mass into r square. That r square is what? Basically it is perpendicular distance. And here r equal to k, you can write this as moment of inertia I equal to m into k square, where m is a mass, k is nothing but what? perpendicular distance, here it is said to be radius of gyration. K is more, mass is further distributed very long from the axis of rotation. K is small, here it is K, the mass is distributed close to the axis of rotation, and that is the meaning. And here this K is said to be radius of gyration. Is that clear? So radius of gyration represents the distribution of mass in the body, and accordingly moment of inertia also changes. Common sense, if suppose this is the K, suppose let us consider this is K, let us consider this is K1, small one is K1, big one is K. Okay, what is moment of inertia? I1, or let's take K1, let's take this K2. For K1, let's consider this moment of inertia I1 equal to what? M is the mass of the ring into K square, K1 square, because it is K1, mk1 square. Second moment of inertia, if the K1 is small, it is K2. Moment of inertia is suppose I2, it is m into K2 square. Mass remains same. Out of these two, what do you think, which moment of inertia is greater, I1 or I2? Common sense, as K1 is bigger, I1 is greater than I2. We can write here I1 greater than I2. I1 is greater than I2 means what? It means what? In case of I1, mass is distributed very far from the axis. Very far from the axis. I2 is less than I1 means what? Mass is distributed very close to axis. And that was represented here. That's why it is said to be radius of gyration. And it is very important to understand the distribution of mass along the axis of rotation that was represented by this thing. Below this topic, there is one blue, sorry, not a blue, it is yellow color shade is there. What they have mentioned, they have given the moment of inertia of a ring, and just they have find out moment of inertia of a disk. So here they have represented two parameters, IR for ring and ID for disk. And if you consider, if you see the both the formulas, they have just mentioned here. As we know, it is mr square for this ring, and disk it is 1/2 mr square. Just we have derived 1/2 mr square. So what they have written here, mk square, because r is equal to k. I have told you here r equal to k, mk square. Just see mk square, and here it is for ring, so kr, and this can be written as mk square, and it is for disk, it is kd. Same thing they have given, but here they have put here they have put r equal to kr. Here they have put r equal to what? R by 2 equal to kd. R by root 2 equal to kd. Now take kd square, r by 2 is 1/2. Here we get same thing that they have mentioned here. So just revise it. Next video we will see the two most important theorem of this chapter, that are nothing but theorem of parallel axis and theorem of perpendicular axis. This theorem are very important to solve some problems. Also, let's understand that in next topic, next video, and then go. Let's see. Remember, you just visualize my video first. While visualizing, it is better if you put the book in front of you. Don't jump directly to third and fourth video. Go one by one. Just see, watch first video first, then second, then third, and finally then go to last one. If you jump directly to last video, you can't understand the basic concepts. I hope you understand this very well. Still, if you have the problem, you can contact. Thank you.